Share screen. So, last class we were talking about peptide synthesis, and we walked through some linear solution phase syntheses, and I think one of the things we were discussing was the more steps you do, the lower your overall yield. No matter how good your steps are, if your yields aren't like 9 plus, your yields are kind of shitty over multiple steps. And so when you're doing a solution phase synthesis like the one we did last class, it makes sense to do a convergent synthesis where you make one component of your peptide, make another component of your peptide, you snap them together. And the reason that makes sense is no one amino acid, no one part of your peptide carries through all of the steps. Why does that help? Well, your yield is based, when you calculate based on a number of steps like we did, it's based on a total number of steps of the thing that had to go through the longest sequence. And if you're able to save any one thing going through every single step because you're able to make one part and then couple it to another part, you cut down your steps. And that's called a convergent synthesis. It underlies an awful lot of medicinal chemistry generally, like small molecule stuff, not just peptide stuff. It's always best if you can combine things at the end. The problem is, to get your yields really high, the best way is to use an excess of reagent. And the problem with using an excess of reagent in solution phase is you then need to remove all the excess of reagent. So every time you do a coupling, every time you do a deprotection, every single step you take, you need to purify your peptide. Because anything you haven't purified can then react in the next step and it can screw you up. So you have to keep cleaning up your molecule every single step, and that gets very lengthy, it gets very burdensome, it gets very difficult. And so nobody does this. I think if it's beyond about a tripeptide, I don't think I've seen anyone who's got decent resources doing solution phase synthesis. So generally what we're going to start talking about today is solid phase peptide synthesis. Okay, there we go. Pop my tablet off. So solid phase synthesis is exactly what it says it is. It means, so in solution phase synthesis, everything is dissolved. In a solid phase synthesis, you use an insoluble bead or an insoluble support. The most common one we use is actually highly cross-linked polystyrene. This is called Merrifield resin. Named after Merrifield, who won a Nobel Prize for this work back in, I think, the 80s. So this has been around a really long time, like as far as, chemistry timelines are concerned. 40 years, and it's really exploded in use in the last 30 years or so, since about the early 1990s. And it's because peptide chemistry advanced to the point where we could actually really make use of this. So what does this look like? There's various versions of this. So I'm going to represent this as a bead. And what this bead essentially is, if we zoom in, is we have a surface with cavities in it. And all these cavities are very hydrophobic. And And because they're basically, this is all of this stuff is made of cross-linked polystyrene. So what this is you take styrene and you add about 1% of divinyl benzoic acid or benzene. And so the styrene polymerizes, and this cross-links additional chains because this vinyl group can take part in one polymer, this vinyl group can take part in another polymer, now your chains are all mixed. And you basically get these beads, but they're irregular, they've got holes in them, they've got gaps in them, they're really, really hydrophobic. And then you have a whole lot of vinyl terminal groups on the surface. And depending on, sometimes they add in other units or whatever, but we functionalize those further. And we get surface chemistry on this thing. And I'm going to talk about the different surface chemistries we can get. So the most common one is called Wang resin. Or Wang resin, named after Dr. Wang, who popularized it. And the idea here is that I'm going to represent these just as the bead and then what it's attached to. Very simple. 4-hydroxybenzyl alcohol. We actually use this all the time for our own chemistry. And you tend to load this on the surface of the bead. Then what you do is you'll often couple an amino acid to it. So an Fmoc protected amino acid with a carboxylic acid. Let's say we use like an EDC coupling. So it's making an ester bond, not an amide bond. AA stands for amino acid, it can be any amino acid. Not NH2, NH-Fmoc. So we have an ester bond on there. Now, this generally gets used for Fmoc solid phase synthesis. We'll talk about why in a second. Then, let's just think about what the nice thing is here and compare this to the solution phase. So let's say I was trying to do the same chemistry in solution phase. Exactly the same chemistry. And let's just protect this. I am going to protect this. We'll stick a TVS group on it. I don't mean anything by writing the Fmoc above it. It's just it saves me space. It just means the Fmoc's on nitrogen. Okay. So in this bottom reaction, what I would do is I would mix the reagents together. Let's say I want a really good yield. I might use an excess of the amino acid. In this case, I probably wouldn't. I'd probably use an excess of this guy because it's cheaper, but whatever. And then I'd use a 5 equivalents to the coupling component because this needs to couple with the amino acids we saw a couple classes ago, or the carboxylic acid. Make the ester bond, done. Except now I have, if this goes to completion, I've got 4 extra equivalents of this amino acid present and 4 extra equivalents of this EDC stuff. And so now I'm going to need to run a column. I'm going to need to clean this up. I'm going to need to do workups. I'm going to need to do all sorts of stuff to remove the unreacted amino acid from the product. That's not a lot of fun. The advantage of solid phase synthesis is you can use the same number of equivalents. When I'm done a reaction, I no longer need to do a workup. All I do is filter and wash. Because I've got solid beads, my product is now attached to a bead. And so I put it into a little filter and I wash it with solvent, and the solvent goes through and it carries all the unreacted material through with it. And all that's left inside my reaction is the beads with my product on it. Now, this is both advantages and disadvantages. The advantage is, holy shit, the workup's easy. I don't need to do columns. I don't need to do any kind of purification to remove the unreacted materials. It's really easy to do. I can get basically pure bead in about 2 minutes after the reaction, compared to maybe 6-7 hours for the solution phase. That's a big advantage. The disadvantage is any impurities that are on the bead, you're stuck with them. You cannot purify them out because you can't remove some. You got multiple spots on each bead. You can't remove some of the beads from the other beads. You can't remove some of the compounds that are on a bead from other compounds that are on the same bead. So your reactions need to be really, really, really high yielding. Because if they're not really high yielding, you'll have impurities on your beads. If you have impurities on your beads, everything starts getting worse because you can't clean up anywhere along the synthesis. The only thing you can do is clean up at the final step once you take it off the bead. So you want your reactions to be 99+%. So you need to use a large excess of reagent because you need to drive them towards completion, because if they don't complete, you're screwed. You have no way to clean them up. So that's basically the advantage and a disadvantage of solid phase peptide synthesis in a nutshell. Let's take a look at what we do with this, though, and sort of why this is so powerful. So if we take that amino acid that we just coupled to a bead and we just used Wang resin, so I'm going to keep the resin in maroon. We add our first amino acid there. Now this peptide, this coupling, this ester coupling can be a little tricky because it's right on the bead and there's often a lot of hindrance and you need to make sure it's complete, otherwise you're going to get a whole mess of things. And so what we often do is we often buy resins with the first amino acid like this preloaded. And you can buy them with every single possible amino acid preloaded. Then we deprotect the Fmoc. And we have deprotected sugar, or amino acids. So now we've liberated the amine. And again, because it's on solid support, we can wash away all this stuff. So as I pointed out when we talked about the protecting groups for amines and things, Fmoc is a real pain in the ass to use. It forms these insoluble plaques. They're really hard to separate once you clean up. They just kind of plug everything. The advantage is if you're doing this in solid state like this, you never need to work up the reaction with the Fmoc. You just drain away your 20% purity solution. It takes the Fmoc crap with it, and it leaves. And so you don't need to worry about impurities sticking around. Then we can couple our next amino acid. And remember, we always write the amino acids N to C, but as we're building this peptide, and I'm going from left to right because it just makes sense to me, we're angling a C to N. So if the sequence is a certain thing, we're kind of building it backwards. Because you'd read the sequence N to C, but we're building C to N. Sorry, I'm going to put that in green. It's a very Christmassy slide. All reds and greens. So we couple it to the next amino acid. And we have another Fmoc. And then we can deprotect. And for 20% purity and DMF. And then look what we get, of course, is we get the free amine. Which then we can put right back into here. It's the same thing, except we're now one amino acid longer. So we couple, we deprotect. We couple, we deprotect. We couple, we deprotect. We couple, we deprotect. Ad nauseum. So where we start getting into trouble is when this gets out to, this works amazing. Out to about 25 amino acids. And then something awkward happens. And it comes back to basically when we were discussing what the difference is between a peptide and a protein. And I think Hazel was the one who brought this up, where the idea is that a peptide, proteins have secondary structure and tertiary structure. Peptides less so have secondary structure. But proteins don't, they're not magic. Like they get secondary structure because the amino acids all integrate with one another. And at about 25 amino acids, if we think about, you know, this hole that's on the resin, we get these peptides, and they kind of stick out. And the reason we use DMF as solvent so much is because DMF has that amide bond that solubilizes the amide bonds of the peptides. And that keeps them sticking out straight instead of folding back in on themselves, because most peptides are kind of hydrophobic, even naturally. And what we're going to do is we're going to protect all the amino acids, because we don't want the amino acids doing chemistry. You can't have any carboxylic acids or amines on your amino acids, because if you do, then they're going to do your peptide chemistry. You don't want them to. And even if you have some sulfurs like thiols or alcohols, theoretically you should be okay, but we tend to keep them protected just because maybe you'll make some thioesters or some esters with the activated acids you're going to put in instead of them react with the amines. And any of that happens will decrease your yield. And anything that decreases your yield when you're doing, if you're doing 25 amino acids, that's 50 steps. That's a lot of steps. Anything that decreases your yield even a little bit is going to cause trouble. And since you can't ever clean up anything on the bead, anything you make, you're stuck with. So you want to avoid all those conditions. So we tend to leave all the protecting groups protected, all the side chains protected. I'm lecturing from home today, so my dog seems to disagree about the need to protect the side chains. I'd like him to see him do it. So the problem is at about 25 amino acids, if we have more or less the same thing, what we're going to start seeing is all the peptides start playing football and sort of do hook plays, and they start folding back on themselves. And that's because you start getting H bonds between adjacent amide bonds. You start making beta sheets. Okay, you start getting secondary structure. That's a problem because now the ends of these things are much less accessible because they're kind of tucked in on the beta sheet. They're not as easily available because they're kind of tucked in around. And that steric hindrance, of course, is going to lower your yield because they're less accessible, so they're less likely to react with the fresh carboxylic acid you're putting in. And so the challenge then becomes, if your yield starts dropping on any individual step, your yields for the overall synthesis start falling off a cliff, and everything gets really, really bad really, really fast. So the way we get around this is two ways, really. Change solvent. So we switch to a much more expensive solvent. This is N-methylprolidinone. Compare with DMF, also abbreviated NMP. They're pretty similar solvents. They're both amides with no hydrogens on the nitrogen and on carbon oxygen bond. And I don't really understand why NMP breaks up these beta sheets better than DMF, but it does. But NMP is a poorer solvent for the peptide synthesis. I don't really see what it can do that the normal DMF can't. It's slightly more nonpolar, so maybe it enters the cavities a little bit better, but I think those would be fully solvated anyways. But it lowers your yields otherwise, and it's much, much more expensive. So what you often see is at about 20 amino acids, syntheses will start ramping up the NMP content. So they'll start adding like 20% NMP, 30% NMP, 40% NMP as you add more and more and more residues. You don't want to jump it up too fast because you're going to lower your yield unnecessarily before you have to. You don't want to jump it up too slowly, otherwise you're going to get these things folding back on each other and they're not going to stay stacked out. So it's this trade-off. The record right now doing this kind of approach is 83 amino acids. And about 30% overall yield, which is outstanding. And there's kind of like, I don't know if you follow these competitions. I do. They're really boring. Well, I don't know. Depends what your background is. Where they're trying to, a bunch of computational chemists get given a bunch of protein sequences and they're told, fold these things. Show me the folded protein. And every 3 years, a whole bunch of people bring their algorithms to the table. It's kind of like robot wars where everyone tries out their algorithms against each other. And you win or you lose. This is where, Google's new AlphaFold 2, which is their entry into the market, did pretty well this summer. I'm suspicious of it. It's got some major flaws, but it can predict simple folded proteins quite well. And there's kind of the same kind of thing for this, where there's kind of a competition to see how high can you go, how many amino acids can you get with your strategies to make longer and longer and longer peptides. 83 amino acids, we're starting to enter into that territory of small proteins at that point. We're trying to make 106 amino acid protein. And I don't think we're going to make it through. We're not going to try to make 83 at once. That's insane. But I think we can make 3 components and stick them together and it's going to work. So, I think these are actually a lot of the components of solid phase peptide synthesis we need to keep into account. What I want to talk about is the problem you have when you're trying to cleave these. So if you look at, I'm going to still see if this is still available. I'm going to share my screen. Give me a second, I'm just going to a commercial website and see this is what I want. Okay, yeah. I'm going to share my other screen. Okay. So, this is Nova Biochem. Actually, for one of the questions that you have, like talk about the different protection groups, this is actually a really good website. They are now owned entirely by Millipore Sigma. And what you can do is, so we have these choices of different building blocks for amino acids. So there's phospholipeptide synthesis, there's bulk amino acids, we'll talk about those, Fmoc amino acids, which are the major ones, all sorts of different derivatives, reagents, some structure derivatives, I'll give some bends, capping agents, and then pseudoproline dipeptides. I'm actually kind of curious on what they got here because we're making some of these things. Oh, there are no answers. Okay, they just kind of just gave up. So if we go to I broke the website. This is not a very good website. There we go. Fmoc definitely dominates. And then I can search by any given amino acid. So let's say I want to look at lysine. Okay. We've got, you can see how these are written Fmoc, lysine, naming the protecting group that's on the gamma lysine. I'm just going to zoom in so you can see this a little bit better. God, these structures are awful. But we have lysine, we have a free carboxylic acid. Notice we're always showing them as the free carboxylic acid. Fmoc group here, different protecting groups on a nitrogen. Here we have an alloc. This is fully deprotected. There's Boc protected group on here. This is kind of the standard. Sort of a modified Boc with a methyl group on a nitrogen. So it's kind of more bulky and blocked. Another Boc protected version. And then sort of an azide lysine with the Fmoc on this guy up here. So you have these varieties of the different things that we can look at, different types of protecting groups. What we'll notice though is that in all cases, basically, if there's an Fmoc on this site here, you're going to have acid labile groups, different forms of acid labile groups like this MCA or Boc, or this is palladium sensitive, but you're never going to see a base sensitive labile group. And that's because what we're doing is we're trying to find chemistry where we can make the peptide using Fmoc chemistry down here, that piperidine coupling stuff I was just showing you, and we can use different chemistry to deprotect these guys. Now, generally, the side chains on any given amino acid is acid sensitive. Fmoc. That's typically the kind of synthetic sort of building block that we have, whatever it happens to be. Doesn't matter if that's a serine, a tryptophan, a histidine, an arginine, an aspartic acid, a cysteine, a methionine. I guess methionine doesn't need protection, but you'll have this kind of layout. So, okay, why does this matter? Well, let's say we built our peptide. So we have our peptide. We used Wang resin, so we'll talk about the other ones in a moment. So after your final deprotection, you'll have your peptide, you'll have an NH2 on one end, it'll be connected to the Wang resin on the other, and you have all these acid-sensitive protecting groups. So what you can do is you can treat this with an acid. The typical one used for this is trifluoroacetic acid. I'm pretty sure we have talked about this one before, but just in case. And that is trifluoroacetic acid. And what happens there is all the acid-sensitive groups have been designed to come off with trifluoroacetic acid, so they all cleave. And your ester also cleaves. Normally it's TFA, a little bit of water, a little bit of triisopropylsilane, sometimes a little bit of phenol. Why do you have this huge mixture of stuff in there? What do they all do? Well, let's just walk through this. So the first thing is the H plus from the TFA will remove a lot of your acid sensitive groups. And we'll come back to why you need these other guys here for a moment. what it'll also do is it'll protonate your resin, or that ester group actually, because the ester is the most basic group there. If you protonate an amine, nothing interesting happens. Protonate the ester, especially on this Wang resin. Get this. And then this can do a 1/6 elimination. What do I mean by that? We start actually pushing arrows, and we get that. So if we follow all those arrows through, oops, we generate that. And then this can then react with any of the nucleophiles that are present in solution. So maybe the water or phenol. Why does it react like this? Well, we've broken aromaticity. Like we broke up the fact this was an aromatic benzene ring. It is no longer a benzene ring. It wants to be a benzene ring. And so it reforms being a benzene ring. And you re-get back your alcohol there. But now you've cleaved off your peptide, and your peptide has a carboxylic acid end on it. So we have an amine and we have a carboxylic acid. We basically regenerated our peptide exactly how we wanted it. So Wang resin, we cleave with TFA, we deprotect all the side groups, we get our product. But there are other options. So we have trityl resin. Normally now it's trityl chloride resin. So you know what, I'll use the modern form. That's the same thing. We got this Wang. Strangely though, what we have at that point now is this. So we can do the same thing, EDC couplings to attach the first amino acid, build your peptide using Fmoc solid phase synthesis. Note when you're doing the Fmoc synthesis, you're doing the deprotections using 20% piperidine and DMF. That's highly basic. And then you're doing a coupling with an excess of triethylamine. That's still basic. So you're always basic when you're making the peptide. The trityl resin is incredibly sensitive to acid. And it's very, very easy to cleave. So we have our resin. We actually use the trityl chloride because it's a little bit harder to cleave than trityl, so it doesn't do it by accident as easily. So we have acid-sensitive protecting groups on our peptide. And then what we can do is we can actually very gently treat this with a really weak acid. So this isn't even a carboxylic acid. This is an alcohol, hexafluoroisopropanol, also known as HFIP, which is a great acronym. 4-to-1 HFIP to water. Sorry, dichloromethane, not water. And this isn't so much protonating the ester. It can't. It's not acidic enough. What it does is it has this hydrogen, how do I put it? Hydrogen bonds, I guess, is the true way of saying it. Very, very distant hydrogen bond. It doesn't need to be any closer because the trityl group just wants to fall apart. And so we generate a trityl resin. Or a trityl cation, sorry. And you have your peptide. This trityl cations, they form spontaneously in even very, very moderate acid. This is incredibly weak acid conditions. So if you want to keep other protecting groups present without cleaving them off, but use acid, you can kind of use this as a very soft acid protecting group, whereas almost all the other ones we're looking at, you use TFA, it cleaves them off, it cleaves it from the bead, everything happens at once. Here you can cleave it from the bead, but still leave all the protecting groups intact. That's pretty useful. The last type of resin that gets a lot of use, I'm not even going to talk about Bock protecting group or Bock chemistry because nobody cares. Nobody uses it. I used to discuss it, but it really, really, really is irrelevant. It's called rink amide, and these three basically account for almost all solid phase peptide chemistry. I don't know where the rink comes from. Slightly more complicated resin, at least apparently. So the other ones were very, very simple. This one is clearly not as simple. Now, one thing to note is we've made all the other bonds to the resin through ester linkages. Here, we're actually going to make an amide bond. So we'll just do the peptide synthesis. And we end up with our product. Oops. So I was saying, if with the Trido one, it made the ester really, really cleavable, and that was because we made this Trido cation. Same kind of idea here. Now I'll do one last one as well, or acid. Sorry, just brain is thinking about something else. So again, if we use TFA, you can imagine those in different color. Liberating a nitrogen. And so what you get at the end of this is it's not really a tridyl, it's a didyl. It's not 3. And it's kind of like a tridyl because it's got those 2 methoxy groups on that carbon, on that benzene ring, so it's really, really, really stabilizing. And I drew one of the methoxy groups in the wrong place for no particular reason. Just migrated. Sorry about that. Plus, you have a peptide, but it's got a weird end to it. So on this side, you have a normal NH2. On this side, you don't have a carboxylic acid, you have an amide. So you'll see these quite a lot, these amide terminated peptides. Now in biology, in your body, they exist, but they're very, very rare. On chemistry, they're relatively common. It's because that carboxylic acid, without it, by blocking it, you do 2 things. One is you make the peptide more hydrophobic, which can be useful as a drug. More importantly, though, you make it more resistant to enzymes that can break down proteins and peptides. So you're reducing sensitivity to peptidases, and that's beneficial. So rink amide makes amide cap peptide. So if you want amide at your C terminus, this is the way to go. Note that although there's an NH2 there, it's still the C terminus. It's still the spot with the carboxylic acid. It's just you don't have carboxylic acid, you have an amide. It's still the C terminus. The amine is the N terminus. It's very easy to get those confused and go, hey, there's nitrogen on that side. It's the N terminus. It's not. It's still the C terminus. Okay. I think I'm just going to check, but I think I covered everything I want to talk about with solid phase peptide synthesis. Yeah. Okay. I think what I might try and do is, in the time left to us, introduce a few ideas about how to couple these things together. So let's say I want to make an 80 amino acid. An 80 amino acid peptide. One way I can do that is decide that what I want is thinking, well, the function of my peptide is somewhere in the middle of the 80. My terminuses don't matter. And normally when your peptide gets long enough, what's on the end doesn't matter. And that's why, with proteins, we're always sticking on purification tags onto the C or the end terminus of the protein. We'll happily stick a flag tag or a his tag onto the end of a protein. If you don't know what I'm talking about, that's okay. And you purify that through affinity chromatography. You remove all the proteins that lack that, and the proteins that have those tags bind to your column, normally only the protein that you genetically engineered, and then you recover it. And yes, you have this extra thing dangling on your protein, but you don't care because your protein is folded properly, and what matters is what the middle of the protein looks like, not what's dangling on the end. Same reason you have people starting to add a lot of fluorescent tags on the end of proteins. You'll add, a fusion protein with a green fluorescent protein or a yellow fluorescent protein or something. So your protein will glow in the dark. It's always dark. And these are actually other proteins that you've attached to your protein. But since they're on the end, they don't affect the way the protein functions. The same thing with the peptide. Since it's on the end, it doesn't tend to interrupt how the peptide functions. Unless, of course, it does, in which case you're screwed. But let's say it doesn't matter what's on the end. So what we can do is make two peptides using solid phase synthesis. Retrosynthesis arrow. So we make the green peptide using solid phase synthesis. Maybe on a rink amide. And maybe we choose strong acid protecting groups. And we have the red one. Maybe on tritol. Note, we could have used the rink amide tritol. So back here with rink amide, this clearly wasn't tritol, but so you still need reasonably strong acid to cleave that. If you add This guy, then this becomes cleavable with HFIP again. And the advantage is, of course, if you have any protecting groups on your peptide, they're not cleaved because you're using really, really, really weak acid, and your protecting groups need TFA to come off. I've never used this bottom one. I know it exists. I think it's been designed and used a couple of times, but I don't know if it's commercially available. But theoretically, fully possible. So we have two peptides. One is rink amide made and it's got protecting groups on it. One is treto made, and you just don't do your final deprotection. You leave the Fmoc on. It does not say Fmoc, does it? So at this point now, you can just couple those two together, right? Using peptide chemistry in solution phase. Is it ideal? No. Is your yield going to suck? Oh God, yes. But you have one carboxylic acid, you have one amine, the two will couple together, and you'll be able to make your extra long 80 amino acid peptide. So another option we have is something called native chemical ligation. I don't love the title because native makes it sound like this is natural, and it's not. This does not happen in nature. So the way this works is, I want to make sure I do this right. We take a peptide. I use Wang synthesis. I get my product. I guess I take amino acids, I do Wang synthesis. So this is just normal Fmoc chemistry. So I leave the Fmoc on. This is Stephen Kent. I believe he's now at Northwestern, but when he did this work, he was at Illinois Urbana-Champaign. Anyways, this is just brilliant. So you take this peptide, you do this coupling, you're done. Now I activate it. So I've cleaved it off the bead. This was on a bead that's now loose. I just activate this. So we'll just use DIC because it's normally one of the stronger activating units, DIPEA, and I've activated my carboxylic acid. Now I need to be careful that my peptide doesn't have any strong nucleophiles present. If they are, they must be protected, and so I must have been careful with how I synthesize this. You'll have the DIC intermediate, which we saw at the beginning of this module. Okay, so we're going to put that to the side for a second. Then what you have is you have a second peptide that is on bead. You have your bead, you have your peptide. And you have your terminus. Actually, I'm going to leave it deprotected to save myself some drawing. You then couple on a cysteine residue. And you pick a very special cysteine residue, kind of an inappropriately protected one. The normal one to use is a benzyl ester like this. And I don't know, you use whatever coupling constant you want. Let's use HATU just for a mix. Using diisopropylethylamine as base. So we have our peptide, we couple our amino acid. And we have our benzyl ester. So far so good, nothing different or exciting or interesting has happened. Now I deprotect. Cover some pyridine DMF, standard conditions take off the Fmoc, I do that. And this is where, depending on how you look at your trouble starts. Because now you have a weak thioester held in close proximity to a free nitrogen. And what you quickly end up doing is doing an acyl transfer. So what was protecting the sulfur is now protecting the nitrogen. Now you have the benzyl group on a nitrogen. And now you have a really good sulfur nucleophile. And this gives us a little bit of a problem, because what happens now is this sulfur nucleophile attacks this activated ester over here and breaks that up. Sorry, I'm sketching out something where I screwed something up. I'm going to take this back. We're going to do this in a second, but I actually don't want to do it here. I don't want to use this protecting group. This is why you don't do this, because I was actually sketching out some ideas for my own chemistry, and my notes are all screwed. Normally you just have a trityl group on here. I'm sorry. I'm really sorry. And then you can actually use just HFIP to take off that trityl group. And I'll highlight that in red. I'm really, really sorry. Just looking at this going, this does not work the way I want it to, and I realized why. So 20% piperidine DMF takes off the Fmoc, HFIP takes off the trityl, and we have a free SH and a free NH2. Well, some team chemistry I was showing. Okay, so your sulfur now attacks this ester. I'm going to start a new slide because this is messy. So I'm going to start by drawing this guy out, and then we're going to have this thioester bond, which is then going to do exactly what we were just showing, but just proper like. Sorry, it's not on a bead. This really, really takes away from the gravitas of the situation by screwing it up. Okay, so we have this situation. I'm actually just going to put the first one in red because it was in red on a previous slide. Okay. So now we have this thioester that's in really close proximity to this nitrogen. And of course, what this does is it makes a new peptide bond. The H comes off water. I haven't drawn the mechanism above, but it's going to be easily picked up. I don't need to worry about it. So overall, what we've done is we made two separate peptides. We then used the terminal cysteine on one of the peptides to trap as a really strong nucleophile, because sulfur is a great nucleophile. It's better than nitrogen, to really, really get a really high yielding reaction. Because again, the problem if we went back to this approach is this coupling will suck. You got two humongous molecules trying to find the acid and the amine, trying to bump into each other the right way. The amine is not nucleophilic. The acid needs to be activated. It's really tough to do. It's really, really hard to connect two polymers together, which is why we're going to talk about some good ways to do that near the end of this course. But connecting two polymers together is nearly impossible. It's really, really, really challenging. And so what we're doing is instead of relying on amine chemistry, we're going to use sulfur chemistry. And the sulfur chemistry is a lot stronger. The sulfur is a much, much better nucleophile. So instead of having an amine looking for this activated ester, we have a sulfur looking for it. The sulfur is much, much stronger. It attacks. It then forces this rearrangement, and we get our desired product. Here. I'm going to leave it there for today, quite a little early. What we're going to cover next class is we're going to cover a few other advances in native chemical ligation. We're going to talk about peptide cyclization And then I'm going to post some reading for next Monday, which is on concepts of click chemistry, which is then really how we're doing this bioconjugation, making these biomaterials and coupling different things together. Because what we're really actually, peptides are pretty simple. We're actually moving to the end of peptides. There's a lot of details in the protecting groups. I'm leaving it as an exercise to ask questions about. It's in the assignment, but it's not particularly complex. And what we're going to discuss then is how we can start putting these different components together and supporting them on different scaffolds, and we can make some new functional biomaterials by using modern click chemistry techniques, which allow us to conjugate really complex things together, like two polymers that don't want to conjugate together. So we need this new chemistry. So next class, it's essentially more of the same. Finishing off cyclization, or finishing off native chemical ligation, talking about peptide cyclization strategies, and then we'll be talking click chemistry and some bioconjugation strategies and how we can go about thinking about making more complex molecules until the end of the course. And then some measurement techniques and some other tools we can use to analyze these kind of polymers and determine their properties. Okay, how about, well, I should ask, any questions about the native chemical ligation stuff or the solid phase peptide synthesis?
So why is it called native?
I don't know. Because you make use of the cysteine, and the cysteine is native, like the cysteine's there, so you're not fully cheating. I have a feeling it's a marketing term, right? I think it should be called cysteine associated dipeptide formation, or cysteine associated peptide coupling. I think that's what it should be called, but maybe that's just too long. So Stephen Kent called it native chemical ligation. Now we all call it native chemical ligation.
Yeah, well, still feels like a little bit like cheating.
It is. We're going to see some more ways of cheating too. Because the problem, of course, with this is where you really, and this is a question I had for a collaborator who wants to make, they want to make cytochrome C. It's 106 amino acids. They want to make a version with some fake amino acids in different places. That's a big peptide. It's really a protein. It is a protein. And you can't make these fake amino acids in place using biochemical methods. Like when I want to make a protein and it's big, I just stick it into a bug and I get the bug to make it for me. That's the best way, as we discussed. But now I want to use unnatural amino acids. And if I want to do that, I can't use bugs. I need to use chemistry, but 106 amino acids is really, really long. As you saw, 83 is the record for a single peptide synthesis. It's too long. Using native chemical ligation, we have gotten up to 120 amino acids. So this can get you higher, which is above where I need to be. But the issue is that then I would need cysteines approximately equally spaced across the peptide, right? Because I would need to have a cysteine present everywhere I want to do this. And this protein doesn't have that. It's got a cysteine at position 16, another one at position 19, and 19 is not 1/3 of 106. And there's nothing at the 2/3 mark. So this isn't particularly useful. So we're going to talk tomorrow or next class about some other strategies that I could use to make that 106 amino acid using alternative forms of native chemical ligation. I'm actually not going to use any of those. I think what we're going to move towards is some of the stuff we're going to talk about on Monday, which is using click chemistry to couple longer things together with very, very high efficiency. We're just going to sacrifice a little bit of authenticity of our sequence. It should be okay. I hope. Man, that was a digression that went nowhere. My wife calls those squirrel stories, where you have a story and it has no payoff. And that story had no payoff, so I'm sorry for that. Okay. Any other questions? Okay, I am happy to leave it there. Have a good rest of your day. I'll post the lecture notes and the video. Those of you who are keeping track with the lecture notes that are already posted, like the full lecture notes, you'll see that we're paralleling them, but not completely. Again, everything here is based on solving the problems in the assignments, so have fun with that. I actually mean that, have fun with that. They're kind of fun problems to make you think. Like, the goal is to make you think. And there is some native chemical ligation questions in there. So we'll talk to you guys later. Have a good day. Bye.